Hi everyone, I hope you're okay and I hope that the videos we keep uploading are helping you out. On this video guys, we will be talking about an addition of a catalyst. Are you together? How does an addition of a catalyst influence a chemical reaction? Are you together? Before we even start guys, let's start by defining a catalyst. A catalyst is a chemical substance that speeds up the reaction without being consumed in that chemical reaction. Are you together? It just speeds up the reaction without being consumed in that reaction. Okay. And its function, guys, is to find an alternative way with a lower activation energy. That's how it speeds up the reaction, because it finds a path with a lower activation energy. Are we together? Let's say you have to travel from position A to position C, but you do not know other routes that will get you straight to position C, and then but you only know a route that will take you to position B first and then go to position C. Are you together? Let's say that's 3 meters over there and then that's 4 meters over there. But now a catalyst will try to find a path for you that will just take you 5 meters only from A to C. For someone who's traveling from position A to C, but they are moving via B because they do not know an easier route, they will travel for 7 meters. Are you together? Let's say hypothetically, for you to travel 7 meters, you will simply need 7 joules of energy. Are you together? For you to travel 7 meters, you will simply need 7 joules of energy to travel for 7 meters. And then a catalyst will try to find a way with a lower activation energy, because this 7 joules, guys, is the minimum energy you need to travel the distance of 7 meters. Are you together? But a catalyst will try to find you a pathway with a lower activation energy. A catalyst can simply find you a way directly from A to C. From A to C, now you are now going to travel a distance of 5 meters. Are you together? And then, since 1 meter represents 1 joules, you will simply need 5 joules of energy. This is now the minimum energy required for you to travel from position A to B with an aid of a catalyst. Are you together? Because without a catalyst, you cannot travel from A to C directly. Are you together? But without a catalyst, you are going to move to position B first and then go to position C. And we'll travel a total distance of 7 meters and we'll need 7 joules. But with an aid of a catalyst, we are just traveling from A to C in a straight line. We will only travel 5 meters, number one, and hence we'll need the lowest amount of energy required to travel that 5 meters. So in addition of a catalyst, it just finds an alternative path with a lower activation energy. Are you together? It finds an alternative path with a lower activation energy, or you can simply say it lowers the activation energy of the reaction. Are you together? So that's what a catalyst does. Okay, let's say we had our chemical reaction. One of the reaction, let's say if the reaction was either exothermic or endothermic, we have our energy over there. This one is for exothermic reaction. If the catalyst is added on this reaction, yes, you will still have the same amount of products, but it will take you less energy to do so. It will take you less energy to do so. Are you together? It will just lower the peak over there and then goes to the same place like that. Are you together? This black curve over here is a curve whenever a catalyst is added. Are you together? Because the activation energy is lowered. Initially, this was the size of activation energy, but right now, after a catalyst was added, this is the new size of our activation energy. It has been decreased. Same applies with an endothermic reaction. If ever you're adding a catalyst on an endothermic reaction, this is what will just happen over there. You still have the same amount of products, but a catalyst will just find a pathway for your reactants to collide without using more energy. That's what, guys, a catalyst does. It lowers the activation energy, or it prefers an alternative pathway with a lower activation energy. Okay, now let's answer these questions. Learners investigate the influence of an addition of a catalyst in a chemical reaction. They decompose hydrogen peroxide. The balance equation, the balance decomposing reaction is given below. So hydrogen peroxide is decomposed into water and oxygen. We are told that learners use copper 2 oxide as a catalyst in one of the reactions. In one of the reactions for the investigation. The table below shows the conditions of the two experiments. Both experiments have the same concentration. Both experiments occur at the same temperature. However, in experiment 1, we do not have a catalyst, and in experiment 2, we will have a catalyst. Are you together? So whenever we have a catalyst, the chemical reaction will be forced, or rather, will be assisted to find an alternative way with lower energy requirements. Okay, which of the reaction will reach completion faster? The one with lower energy requirements. Experiment 1 will reach completion faster. They could have said which one of the experiments have a higher rate of reaction. The one that has a higher rate of reaction is the one that will reach completion faster. So experiment number 2, the one that has a catalyst, will simply reach completion faster. We are supposed to use the collision theory to justify our answer. Okay. An addition of a catalyst, which is copper 2 oxide, will lower the activation energy of the reaction. Are you together? An addition of copper 2 oxide, which is a catalyst, will simply lower the activation energy of the reaction, the activation energy of the reaction. Or you can say that an addition of copper 2 oxide, which is our catalyst, will take an alternative pathway with a lower activation energy. Are you together? So if now, guys, the activation energy is lowered, it simply means that more colliding particles will have the kinetic energy that is greater than the activation energy. Are you together? And hence now more particles will result in effective collisions, and hence the rate of reaction will increase. Or rather, we can say hence the reaction will simply reach completion faster. Are you together? An addition of a catalyst, guys, will lower the activation energy of the reaction, or you can say an addition of a catalyst will take a different pathway with a lower activation energy, and hence more particles will have kinetic energy which is greater than the activation energy, and then more particles will simply result in effective collisions, and hence the rate of reaction will be higher. Or the last statement will simply say, hence the reaction will reach completion faster. Okay. And then now we are told that the sketch below represents the Maxwell-Boltzmann distribution curve. Obviously, guys, always the time on the Maxwell-Boltzmann distribution curve. On the y-axis, you have your number of particles. X-axis, you simply have your kinetic energy. Use the sketch to indicate the influence of a catalyst. A catalyst, guys, will simply lower the activation energy. So we'll just shift the activation energy to the left. This will now become our new activation energy. Remember that, guys, initially these over here, that's when you'll find effective collisions only. But with an aid of a catalyst, effective collisions are also found over there. Are we together? The pool of effective collisions will increase or will be more. That's how, guys, we're supposed to indicate there by just drawing the line of our new activation energy. And then we are told that the graph below shows the amount of oxygen that was collected. Okay, which experiment is represented by curve X. Curve X is the one which is less steeper, and secondly, curve X is the one that will reach completion later. That means curve X is the reaction that did not have a catalyst. So curve X is simply experiment 1. Curve X is experiment 1. Why? It is less steeper. That means the rate of formation of our oxygen was slow. And secondly, it reached completion later on after 8 minutes, whereas the other experiment reached completion after 4 minutes. So experiment 1 is represented by curve X, and experiment 2 is represented by curve Y. That's experiment 2. Okay. So if the volume of oxygen collected is 0.54 cubic decimeters, calculate the rate of production of oxygen if the molar volume of a gas is 27 cubic decimeters at 40 degrees. So they want us to find the reaction rate in moles per second. So that means we must find remember that, guys, for us to find the rate of reaction, our rate of reaction is always equal to the change in the quantity of products all over change in time. Are you together? The quantity of products they want us to focus on is the moles. So it's the change in the number of moles of products. In this case, we can say the number of moles of oxygen. The change in the number of moles of oxygen all over time. Okay, since oxygen is a gas, we can simply use the formula that says the number of moles of a gas, which is oxygen, is basically the volume of the gas divided by the molar volume at a specific temperature. That's basically 0.54 divided by 27, and this will simply give us 0.54 divided by 27. This will simply give us 0.02 moles. So these are the number. Therefore, I can conclude that the number of moles for my oxygen gas that were formed is just 0.02 moles. I formed 0.02 moles. Are you together? So they wanted me to find the rate of if the volume collected, calculate the rate of reaction. They did not tell me that's in which experiment. Okay, let me just include it there. In experiment 1, or let's say experiment 2. Yeah, we are calculating the rate of reaction in experiment 2, right? This amount of oxygen, we collected it in 4 minutes in our second experiment. Are you together? It took just 4 minutes to form 0.02 moles of oxygen in experiment number 2, but it took 8 minutes to form this amount of moles of oxygen in experiment number 1. So they want me to find the rate of reaction in moles per second. That means my quantity should be in number of moles and my time should be in seconds. Since I'm looking for experiment 2, the final number of moles of my oxygen, I simply had 0.02. The initial number of moles at the beginning of the reaction, I did not have any oxygen, so it was 0 over there. And then the amount of time is just it's 4 seconds, very. I thought it was minutes. So it took 4 seconds to form oxygen in experiment 2, and it took 8 seconds to form oxygen in experiment 1. So over here I simply have 0.02 minus 0 divided by 4, the total amount of time. This will simply give me 0.005 moles per second. That's how, guys, you should have found your rate of reaction. Eh? Or if your calculator was in scientific notation, it was just going to be 5 times 10 to the power negative 3 moles per second. That's how, guys, you're supposed to deal with these calculations over there. So please, guys, do stay tuned and wait for more videos. Thank you.